We will now discuss an important law that is used in solving network of circuits. If you have a large number of resistors, capacitors and so on connected in a complicated network, how do we find the current and potential difference across each component? Kirchoff's laws are very useful in solving network of circuits. So we will spend some time looking at Kirchoff's laws. Kirchoff's laws are applied for networks of circuits, and there are two statements for Kirchoff's laws. Statement number one: the algebraic sum of currents meeting at a junction is zero. Well, it is not a very difficult thing to understand. Now, if the current reaching a point is positive, the current leaving a point is negative. In other words, the total amount of current reaching a point equal to the total amount of current leaving. Is that right? If you add the amount of current reaching a point to the amounts of current leaving the same point, the total sum will be zero. That is the meaning of the first law. The second statement is, in any closed circuit loop, the algebraic sum of the potential drop is zero. Well, that needs a little explanation. So let me explain that after, of course, talking about the statement one. Statement one says the algebraic sum of currents meeting at a point is zero. So in here, I1 is the current that reaches the junction A, I2 and I3 leave that junction. That means the current reaching a point is positive and the current leaving that point is negative. So what happens if you add I1? Then if I1 is positive, I2 and I3 are negative. Therefore, the first law applied to junction A will be I1 minus I2 minus I3 equal to 0. Well, we have one equation. Using these statements, we can form any number of equations and solve those equations for the unknowns. Okay, let's now talk about that second statement, the second law. The second law is applicable only for closed circuit loops. Well, here is a closed circuit loop. Now, if any part of the diagram cannot be read, I would want you to keep the printed PowerPoint with you. Now, here we have a 2 ohm resistor, a 5 ohm resistor, and a 4 ohm resistor are in parallel. We have a cell or a battery of EMF 6 volt in this part of the circuit. Well, let's try and use this to explain the second law. Alright, pay attention to this. Sometimes it could be a little difficult to understand. So try and see whether you understand the concept. In the figure, A, B, E, F, A. Look at the way I have named it. This is a closed loop. And the way I have taken that loop is counterclockwise. You understand the counterclockwise, the direction opposite to the motion of the hands of a clock. Look at this. A, B, E, F, A is a counterclockwise loop. If I name it the other way around, A, F, E, B, A is a clockwise loop. How about this? B, C, D, E, B is another counterclockwise loop. So when you name a closed loop, you must pay attention. Am I taking a counterclockwise loop or a clockwise loop? There is difference in there. Now, A, C, D, F, A. Look at this. A, C, D, F, A is at another closed loop. Tell me, is this counterclockwise or clockwise? A, C, D, F, A. Well, that is also counterclockwise. On the other hand, if I had taken it this way, A, F, D, C, A, that will be now clockwise. Okay. The second law is applicable to all these closed loops. What does the second law say? The second law says the algebraic sum of the potential drop in a closed loop is 0. Well, look at this. What is the potential drop across a resistor? Can anybody tell me that? What is the potential drop across a resistor? V equal to Ri. The potential drop across a resistor is the current multiplied by the resistance. What is the potential drop across a cell? The potential drop across a cell is its EMF. Well, we are only using resistors in here. We are not using capacitors. But if you use a capacitor, can you tell me what is the potential drop across a capacitor? V equal to Q over C. Have you forgotten that? Well, fortunately, we are not going to use a capacitor in these circuits for this class. Okay. Well, in the next lesson, I will do that. The direction of closed loop can either be clockwise or counterclockwise. So when you name a loop, it is important to identify, is this a counterclockwise loop or a clockwise loop? The direction of a closed loop can either be clockwise or counterclockwise. The loop A, B, E, F, A is counterclockwise, whereas A, F, E, B, A is clockwise. The loop B, C, D, E, B is counterclockwise. Now, I want you to watch the direction of currents in each of the resistor. Look at the direction of the loop here. B, C, D, E, B. Now, this is the direction of the loop. If you look there, the direction of the current in the 4 ohm is the same as the direction of tracing the loop. Is that right? Whereas the direction of current in the 5 ohm is opposite to it. Well, that is very significant, because if the direction of current in a resistor is the same as the direction of tracing of the loop, then the potential drop across the resistor is positive. On the other hand, if the direction of current in a resistor is opposite to the direction of the tracing of the loop, then the potential drop across that resistor is negative. Did you understand what I said? Look at this again. The loop B, C, D, E, B. Now look at the way my pointer moves. It is traced in the counterclockwise direction. The direction of the loop is the same as the direction of current in the 4 ohm, but it is opposite to the direction of current in the 5 ohm. Do you see that? That means when you trace out the loop B, C, DEB, the potential drop across the 4 ohm is positive and the potential drop across the 5 ohm is negative. Very important to know that. In applying the second law to a closed circuit, we will define a loop that is either clockwise or counterclockwise for the circuit and use the convention described in the next slide. And that is the convention I was talking to you about. I'm going to put down that convention for you. What is the convention for assigning the sign of the potential drop? This is the convention. If the current in a resistor is the same as the direction of tracing of the loop, then the potential drop across the resistor is positive. That's not difficult to understand now. If the direction of tracing of the loop, I'm tracing out the loop now and watch it, is the same as the direction of current in a resistor, then the potential drop across the resistor is positive. In the 4 ohm, the direction of current and the direction of tracing of the loop are the same. The potential drop across the 4 ohm is positive. On the other hand, the direction of tracing of the loop is opposite to the direction of current in the 5 ohm. The potential drop in the 5 ohm is negative. If the current is opposite to the loop, the potential drop in the resistor is negative. And that is how you assign the sign of the potential drop across a resistor. Now, and you know the potential drop across a resistor V equal to Ri. How about the potential drop across a cell? How do you know if the potential drop across a cell is positive or negative? When you take the algebraic sum of the potential drop, it is very important for you to know whether a quantity is positive or negative. Now, look at the convention we are going to use to see if the potential drop across a cell is positive. If the loop is traced from positive to negative through the cell, the potential drop across the cell is positive. For example, look at the cell here. If I trace this loop A, F, E, B, A, that loop is traced. Now when it comes to the cell, that loop is traced from positive to negative through the cell. That means its EMF or the potential drop across that cell is positive. On the other hand, if we are using this loop A, B, E, F, A, now how is this loop traced through the cell? It is traced from the negative to the positive. I hope that is clear. The loop A, B, E, F, A is traced from the negative to the positive through the cell, and in that case the potential drop across the cell will be negative. If the loop is traced from negative, when you trace out the loop, if it goes from negative to positive through the cell, then the potential drop across the cell is negative. Now, before you move on, you need to understand the sign convention. Then only you move on. So stay here and watch it maybe a couple more times to understand the sign convention. The direction of tracing of the loop, if it goes from negative to positive, the potential drop across the cell is negative. On the other hand, if you trace out the loop like this so that it goes from positive to negative, the potential drop across the cell is positive. and of course the potential drop across a cell is its EMF.